So in the previous lecture, we introduced the idea of an instrumentation amplifier. Where is it used? It's a differential amplifier. The characteristic, the unique defining characteristic of an instrumentation amplifier is it should have a very good common mode rejection or a very high PSRR. This is the one defining characteristic of instrumentation amplifiers. And of course, other things is high input impedance, and preferably anytime you have a differential circuit, it should exhibit some kind of differential symmetry. And programmable gain. These are the things we need in an instrumentation amplifier. Its instrumentation amplifier is just a differential amplifier, okay, with an added condition that its CMRR has to be exceedingly high. Now what we will do in this lecture, we will take a different realizations of the instrumentation amplifier and analyze whether it meets all these conditions or not. And then finally, we'll arrive at the most popularly used instrumentation amplifier architecture. So let's start with the simplest instrumentation amplifier, which is our voltage subtractor with a gain. We have already discussed this circuit. It's a voltage subtractor. If you apply a node voltage V2 here and V1 here, apply superposition, you can easily show the gain for V1. If I assume V2 is 0, it will be minus of R2 by R1 times V1. If I assume V1 is 0, and let's assume the output due to V2 is VO2, that's given by R2 by R1 plus R2. That's the voltage at this point. Then from there onwards to the output, it will be a non-inverting amplifier, 1 plus R2 by R1, and you will get the gain to be R2 by plus R2 by R1 times V2. So you add the two, you get this expression. So it's V2 minus V1 into R2 by R1. So ideally, if all these resistors are exactly matched, see, remember, V2 is going through this path. It's first coming through this resistive divider and then it's getting amplified. V1 is going through amplification due to R1 and R2. Okay, these resistors are different. If these resistors are identical, if R2 is exactly equal to this R2 and R1 is exactly equal to this R1, then the common mode gain is 0. Okay, CMRR will be infinity. But in practice, no two resistors are identical. There will always be some mismatch between the two resistors, and these mismatches depends on the type of the resistor and also how the resistors are fabricated. If you fabricate them inside a chip, the mismatches will be due to doping concentrations, the material used. Okay, that's mainly the properties, right? Properties of the resistor. Doping concentration will dictate its resistivity and all that. So, and also the dimensions of the resistor. So these things will dictate matching between two resistors. So in the presence of matching, we will then find out, in the presence of matching errors, we will find out what the common mode gain will be. And also very quickly, anytime we take a circuit like this, we will find what its differential gain is and common mode gain is. Differential gain, we already analyzed. It's very simple. Assume we apply Vd by 2 and minus Vd by 2 on both the nodes. V2 is Vd by 2, V1 is minus Vd by 2. Then the differential gain is simply R2 by R1 times V2 minus V1, which is Vd itself. It's simply R2 by R1 is the differential gain for the circuit. For common mode gain, ideally it is 0, but we have to assume mismatches. Only then you get a finite common mode gain. So we'll assume the resistors R2 is slightly mismatched with the feedback resistor R2, and R1 is also slightly mismatched by a factor delta R1. Okay. Now, using a little bit of mathematical analysis, you have to now derive, assuming this node voltage is, we are applying the same VCM and DCM to both these nodes, we'll have to try to find the output voltage. I'll leave that as an exercise and quote you the final result. You can finally arrive at the expression for the common mode gain of an amplifier, which depends upon mismatches between the resistors, delta R and delta R1 and delta R2. The CMRR again can be written in this format. Okay, delta R2 times R1 by R2 minus delta R1 by R1 plus R2. Okay, it's a very simple analysis. You guys can carry out yourself. I'll just show this once. You can take a snapshot and look at it, stare at it, and it will be very simple. It's just KCLs and KVLs. At this point, since we have analyzed so many op-amp based circuits, this should be a no-brainer. Okay, so I'll leave this. So all I'm showing here is that the CMRR depends upon the resistors. Okay, and therefore it depends on how well the resistors are matched. The resistors R1 and R2 are supposed to be matched really well. If they are not matched, then you have CMRR, finite CMRR. If you are looking at the orders of CMRR in the orders of 140 decibels and all that, you need really great matching. Okay, so whenever you want great matching, you try to manufacture those resistors closely in a single chip itself. So you can't have them as external resistors. So if you look at this amplifier circuit, if I want great matching, so we just showed that the CMRR of this circuit depends upon matching between these two resistors and these two resistors. So if I want to minimize or offer significantly lower CMRR, then this entire thing should be enclosed in a single chip. Inside a single chip, these resistors can be well controlled. I mean, you can take care of it in layout, how do you lay out the resistors, and also maybe some fabrication techniques, to ensure that the matching between the resistors is as good as possible. Okay, so the conclusion, take home point here is that the CMRR of the circuit depends upon the matching between the resistors, and therefore they have to be all internal. Now, if they are all internal, then we have a problem. What is the problem? I said that when we talk about instrumentation amplifier, I need programmable gain. If I have to give you programmable gain, either resistor R2 has to be external or R1 has to be external. Okay, the moment I make R2 external, let's say I make R1 external, R2 external, then R1 will be internal to the chip. Okay, so what I've shown it in the pink dotted lines is the chip the chip contains an op-amp and two resistors. These two resistors R2 are external to the chip. Okay, so now you give this pin as an external pin to the chip, and you connect a resistor R2. Now the user, the circuit designer, will be connecting the two external resistors R2 to achieve gain programmability, right? The gain of the circuit is simply R2 by R1. That's the differential gain. I want programmability in this. I can either vary R2 or R1, and whichever you want to vary, you keep the resistor as an external resistor. Okay, and you give the freedom for the user to vary that. But the moment I keep it as external resistor, I run into the trouble of matching. Okay, matching becomes very difficult if you want to take external resistors. These two resistors will have very poor matching. So therefore, poor matching leads to poor CMRR, and therefore adding programmability makes it complicated, makes it impossible, because your CMRR will be degraded. So this is not a great architecture within itself. Okay, it is great provided if R2 and R1 are internal. If they are all, let's say this entire thing is in a single chip, it's great. You can control how well resistors are matched. You can lay it out very closely. You can also take some design steps at fabrication level to ensure that the matching is really well. Okay, the matching is really good. So your CMRR is very, very, very high. Okay, but programmability is a problem. The other problem with the circuit is input impedance, right? So input impedance is supposed to be infinity. For this circuit, if you guys were to analyze the input impedance of this circuit, how do you find input impedance? You have to find for each path. So first you can assume V2 is 0 and find the input impedance seen by V1. Then the circuit simply reduces to a inverting amplifier, since the resistors R1 and R2 here, right? These two will come in parallel, and they will be connected to ground. No current flows into the op-amp. I can treat it as ground. It will reduce to an inverting amplifier, and the input resistance seen by V1 is R1, and the input resistance seen by V2 is R1 plus R2. Okay, it sees both these resistors in series, so it will be R1 plus R2. So that's the difference between. Now one thing, the input impedance itself is not symmetric, and that's not a good thing for a differential amplifier. Okay, so if you are connecting it to a circuit with a poor source resistance, this itself, the input impedance mismatch, even if you assume R1, R2 are all ideal, that can cause some common mode variations. The circuit can end up responding to some common mode variations. Okay, see, keep in mind, how do you get zero common mode gain? The differential paths, the signal paths for V1 and V2 has to be more or less the same. They have to be identical as you reach the output port. You start from V1 and reach the output, start from V2, reach the output, the path should be more or less the same. Okay, they should look almost identical. Then you get nearly zero common mode. But here if you see, the input impedance itself is not same. The signals go through very different paths, therefore very different, the paths which look very different. Okay, therefore the input impedances will not be same, and it's not a good differential amplifier. So let's take another circuit. See, all I need to do is take difference between two voltages and amplify them. So what I'll do, I'll start with a inverting amplifier. This guy here is an inverting amplifier, and then use it in the adder mode. So instead of connecting voltage V2 here, I'll apply minus V2. So if I apply minus V2 to an adder, so this circuit is, if you see, right, this part is an voltage adder. And the gain of the circuit is given by minus of R2 by R1 into V1 minus V2 with a minus sign, overall minus sign at the output because it's inverting. Okay, and V1 plus V2, V1 plus, let's call this node as Vx, it's V1 plus Vx. And Vx here, if you see, I'm using another op amp to invert it and generate minus V2. So you get V2 minus of V2 minus V1 by R into R2 by R1. So this is not right here. So it will be V2 minus V1 times R2 by R1. So the differential gain of the circuit, which is, if I assume, if I apply a differential input at V2 and V1, is R2 by R1. That's the differential gain of the circuit. Ideally, the common mode gain is 0. But now if you see, right, it's two different paths itself. There is one path here, and for one signal, and this signal's path is different. Okay, so I have a problem here with common mode because the circuit doesn't have any differential symmetry. Okay, second problem, input impedance. So I'm just counting what are the problems with the circuit. What about the input impedance? The input impedance seen from V1 is R1. Similarly, the input impedance seen at V2 is also R1. That's good. Okay, depending on, these two resistors are different resistors, so there will be some matching errors. But I can somehow, put all these things in a single chip. Let's assume I'm somehow ensuring that matching is ensured, and I get pretty decent matching. But still, input impedance is non-zero. First of all, you get matched input impedance, okay, R1 and R2, but the main R1 and R1, but the problem is it's finite. Ideally, you want infinite input impedance. So input impedance is poor in this case, and the circuit doesn't really have a pure differential symmetry. So whenever you want CMRRs in the order of 140 decibels, the circuit needs to have some form of differential symmetry. Okay, and the gain, for example, this circuit, the gain is given by minus of R1 by R. If these two resistors don't match exactly, that will lead to a gain being not equal to minus 1. So if the gain is not exactly equal to minus 1, then you end up creating a path for common mode. Okay, because if it's not, then if you apply, let's say you apply VCM here, you would expect minus VCM to appear here, but it will be minus of some alpha times VCM. And here you will have VCM. So if you find out the common mode gain for the circuit, it will be VCM into 1 minus alpha. Okay, VCM into 1 minus alpha times R2 by R1. So now if you see, common mode gets amplified, and if alpha is not equal to 1, you will have some residual common mode output signal. So it's not purely differentially symmetric. That itself rules it out. If you need high CMRR, it should have some differential symmetry for both the input signals. Second thing, the circuit has poor input impedance to begin with. That's another big red flag. So that's also not a great that's also not great for it to be used as an instrumentation amplifier. Third thing, programmability. Can I add programmability in the circuit? if I were to add programmability, if you look at the differential gain, it just depends upon the ratio of R2 by R1. Which resistor do you think will you make it programmable? Meaning one resistor you'll have to make it external to the chip. I don't want to touch R1 because R1 matching is important, because there are two R1s here. These two has to be matched. These two has to be matched. So I don't want to put them external, because if I put them external, then matching becomes critical or complicated. So I don't want to do that. So instead, R2 will be external. That will be the programmable resistor. Since R2 is a single resistor and it doesn't have to be matched to any other resistor. Okay. So I don't have a matching problem here. Remember previous circuit, when I made R2 external for programmable gain, I had to match it to another resistor R2. Okay, there were two R2 resistors. Here there is only one, so there is no problem of matching here. So great for programmability. Programmability, it's great. I can just vary one resistor and achieve programmability. I can keep the resistor as external. Okay, I can just take these two pins out. Okay, see, think like this. You are an engineer who's now designing an instrumentation amplifier chip. So you are going to put these op-amp inside a chip and these resistors also inside the chip, and you will give this as external pins for the user to use, and you will sell this whole thing as a single chip. Okay, and call it as instrumentation amplifier. You can ask me, I mean, why can't I just build the circuit using op-amps on a printed circuit board or a breadboard? Remember the same problems. Anytime you make it external, the resistor matching becomes problematic. And these two amplifiers, they also needs to be matched very well. Okay, so then again, I can't use them. Making them external, we will later see how op-amps gain can also impact common mode CMRR. So these op-amps gains also matter. So we have to match the op-amps also. Preferably we have to match the op-amps as well. Okay, so all that can be easily done if you put all these things on a single wafer, single silicon wafer or a single chip. So you keep only resistor R2 external, I get great programmability. So this circuit, the only advantage that circuit offers is great programmability. Okay, so now we have to combine, see, slowly as I'm discussing more and more circuits, think about it. You have to try to combine the best of all these circuits. So this circuit, the good point about the circuit is resistor programmability. I just have one single resistor, and you have to think of an architecture where you just have to vary a single resistor for gain. But what are the problems with this architecture? Poor input impedance, no differential symmetry. So these are the problems that we have to solve. So we look at other architectures as well, whether it's solving or not. Now let's take another architecture. Here the inputs are applied at the non-inverting terminals. So obviously you can directly see this is trying to solve the problem of input impedance. Input impedance is infinity for both the inputs, and they both are looking at the positive terminal of the op-amp, symmetric in nature. Great. As far as input is concerned, they are symmetric. That's it. But now the signal parts, if you are to find the gain of the circuit, I'll let you guys analyze it quickly and tell me what will be the gain of the circuit. I mean, we have done such circuits so many times, so I'll analyze it very fast. So you can apply principle of superposition. Okay, so start finding gain for V2. If you want to find gain for V2, I'll assume V1 as 0. If V1 is 0, this one here is an non-inverting amplifier. This node will come to 0. So this V2 will see a non-inverting amplification. So V2 will be given by, V2 will see a non-inverting amplification. So V0 is given by V2 into 1 plus R1 by R2. Okay, that's the gain due to this. V2 into 1 plus R1 by R2. Now we have to compute the gain due to V1. So I'll assume V2 is 0. If I assume V2 is 0, now V1 is present. The first stage is a non-inverting amplification. So it will be plus V1 into 1 plus R2 by R1. The second stage, if you guys see this, it will look like an inverting amplifier with a gain of minus of R1 by R2. The gain is minus of R1 by R2. Okay. So now if you add these two, you will end up getting V2 into 1 plus R1 by R2 plus V1 into 1 plus, again this will be R1 by R2. You can easily show that it will be 1 plus R1 by R2 with a minus sign here. So what you end up getting, the overall output is simply V2 minus V1 into 1 plus R1 by R2. Okay, again if these resistors R1 and R2 are matched, perfectly matched, then the common mode gain of the circuit is 0, ideally 0. But if I assume R1 and R2 are not matched, so if R1 has a finite error and R2 is R2 plus delta R2, that will lead to common mode errors. Again, matching is very critical. So ideally you would want to prefer, again you can derive equations and show that because the V1 goes through a different signal path compared to V2, there are going to be some common mode errors. So ideally if you want to minimize common mode gain or maximize CMRR, ideally you would want this entire thing to be in a single chip. Okay, and then you try to control matching by choosing the right dimensions, area, layout techniques and fabrication techniques. You try to match these resistors as well as possible. Remember, for you to get this proper differential gain, you need to match this. If everything has to be inside the chip, we have a problem of programmability. Okay, programmability in the gain becomes problematic. Second thing, the circuit doesn't have differential symmetry, meaning there is no the paths for the input. Two differential inputs are not the same. If you recall from our analysis of differential amplifiers, differential circuits exhibit what we call as the half circuit symmetry, meaning when you look at the circuit, when you traverse from input to the output, more or less the circuit, both the paths will be same. Okay, for the signal paths from both the inputs, both the differential inputs will more or less be the same. This doesn't have that. Okay, there is no differential symmetry. Input impedance is good, but and the third most importantly, I cannot have programmability here, because then if I have to add programmability, then I'll have to keep two of these resistors external. Okay, apart from that, the main problem here is no differential symmetry. That itself is a big no, because see, we will later analyze the impact of op-amps gain on CMRR, and there you will clearly see why I am stressing this point, differential symmetry. Okay, so op-amps gain will also matter, and we will see how it matters. So usually when you are designing a differential amplifier, it's preferred to have good differential symmetry. Okay, so as far as programmability is concerned, this is not great. As far as input impedance is concerned, it's great. Okay, so we have analyzed 3 circuits so far, and we found out the input impedance is one circuit is good. In the previous circuit, we found out that programmability is great. I can just vary one resistor and get the programmability. So now we have to see slowly, can we combine, and also we saw that this circuit, the circuit shown here, and the previous circuit did not have good differential symmetry. The input signal was going through completely different paths. So we'll try to address this and come up with a different architecture to fix these problems. And that is what I've shown here. So the first stage, the second stage, that is the familiar differential amplifier we discussed in the beginning of the lecture. A simple subtractor with a finite gain. What I'll do, I'll take that circuit, and then instead of applying the input signals as it is, I will pass it through 2 buffers, 2 voltage followers, and feed it as an input. Now the circuit is good, has good differential symmetry. The signal paths are, it goes through the same op-amp and comes at the output. Okay, there is some kind of differential symmetry in the circuit. Okay, it's more or less there is some axis of symmetry around which the circuit has some kind of symmetry. Input impedance is infinity. That is also great. Your input impedance is very high, good for voltage amplifiers. Okay, the only problem with this circuit here is programmability. Okay, I cannot see, if I have to great CMRR, then these resistors have to be well matched, which means I have to place them inside a single chip. I can't make them external. But if I want programmability, I need them to be external. So I need to come up with a way that I include programmability somewhere else and still maintain the differential symmetry and the input impedance, high input impedance. Okay, then I have finally arrived at the right architecture for the op amp. So I'm not deriving the expression for voltage gain for this. This is very simple. So if I find V naught, it's simply given by V2 minus V1 times R2 by R1. And we can easily show that the CMRR will only depend upon the matching between these two resistors and these two resistors. In fact, we haven't considered op amp's gain into account. Op amp's gain, these two op amps need not be exactly matched. That can also cause some matching errors. We'll talk about that in the later lectures. But mainly resistor matching is a bigger concern, and you would prefer to have all of them inside a single chip. So when you put all of them in a single chip, then gain programmability becomes a challenge. Okay. So one of you are asking, why not just add a different stage for a gain? So you want to minimize as many components as you can. Okay. And have the circuit as differentially symmetric as possible. So there is this stage is a differential to single-ended converter. You can picturize it like that. You can picturize this guy like a differential to single-ended converter. Until this, if you can maintain differential nature, we are good. Okay. So think of it like that. We will talk about that in the next lecture when we start discussing a proper instrumentation amplifier that's commonly used. You will see it combines the best of all these things. Okay. So that's it for the different instrumentation amplifier architectures. In the next lecture, we'll arrive at the most optimal and the most commonly used instrumentation amplifier architecture.